In Module 6, we're going to see the form method, first order reliability method, on how to estimate the failure probability using a linear approximation of the limit state function and knowing the full distribution, the full joint distribution for f of x, the PDF for the random variable involved in my reliability problem. So if we look a little bit of the nomenclature, we have again x, which is going to be our vector of random variable involved either in the resistance or solicitation model. We're going to have f of x, their joint distribution. G of x is my limit state function, the function that is positive in the survival domain, negative in the failure domain. And speaking of it, omega is my failure domain. So all the values for which, again, my limit state function is negative, where my domain doesn't, where my system does, or my component doesn't satisfy either the service or safety limit state functions. Then I have g of x equals 0, which is going to be my limit state surface. So here, this is going to be my frontier between my failure and my survival domain. What we see here is my joint density, f of x, the same here, my limit state function. We have my marginal and the joint, as I said here. So the problem we're trying to solve with form, so what do we do when our vector of state variable is large? We can't plot it anymore, and it's not going to be possible to integrate to evaluate what is the volume or hypervolume under my joint PDF that is in the failure domain. So in those cases, we saw in module 5, we could use MCFOSM or FOSM, but we didn't consider the full distribution. We only considered it was a jointly normal distribution that was describing our random variable. In the case of form, what we're going to see here, we're going to consider the full joint distribution that is not necessarily going to be normal. So form, the acronym for first order reliability method, is going to be a first order method, so a linear approximation of my limit state function, but considering the joint distribution using a variety of cases. It's going to be the most general methods we're going to see here, at least the most general in terms of linear approximation. So with FOSN that we saw in module 5, we were making the assumption that we only knew the first two moments of my joint distribution, which was akin to modeling it as a jointly normal distribution. We're not going to do this approximation in form anymore. So the first thing we're going to need to see is how can we transform from original space X to the standard normal space U, where we're going to do all of our calculation. Because as we did with FOSM, we want to use a linear approximation of my limit state function, g of u, in the standard normal space, in order to minimize the approximation error. But we're going to see in all generality, how can we transform from an original space X to the standard normal space U? So in introduction, this is what we just covered. We're going to then see how can we see all the cases where we can linearize from an original space to a standard normal space in the context of structural reliability. That's going to set the basis for the form method. And we're going to see, for example, corresponding to the four transformation case. The first one is going to be normal to normal. Second one is going to be prescribed marginal distribution. That can be anything, but that are independent. So we can model the joint by the product of the marginal. Third case is going to be a Morgenstern joint distribution. Fourth case is going to be a Nassau joint distribution. So that places us here at module 6, which is the form method. So in terms here, we see this is a modern race car, which is a method that's going to be really fast and that's going to be fairly accurate. But if we compare it to Monte Carlo, we need to satisfy some hypothesis if we want to use this successful. So we start with the transformation from original space to standard normal space. So we're going to do a quick recap of what is the standard normal space. How can we transform in a general case from the original to the standard normal space? And we're going to see our four case, normal, the prescribed marginal but independence between my dimension. We're going to see Morgenstern, and finally for Nassau. So if we start with the recap about the standard normal space, we're going to say U is an n-dimensional standard random vector. So this is going to follow here a standard normal n-dimensional distribution, which is going to be simply a multivariate Gaussian with mean zero and unit variance. So as a property, the contour of that multivariate standard normal as a spherical contour, in the case of two-dimensional, it's going to be circular contours, where if I take slices in any direction, the slices are going to look like Gaussian distributions. So, and in all direction, as I'm getting away from my origin, that 0, 0 center, my probability content is going to decrease exponentially with increasing or distance from the origin. So we use that standard normal space in the context of probability theory because the failure domain omega that is bounded by a plane, the probability content on one side of the plane is fully defined by the distance between the origin and that plane. So it means that the probability that my standard normal space belong to the half space omega correspond to the integral over the domain omega of my integral of my joint PDF in the standard normal space. And this integral can be boiled down to simply the CDF of minus beta, where beta is the distance between the origin and that half plane. Whereas this integral, which corresponds to my probability of failure, is entirely equal to what I would obtain by integrating in the original space. Okay, but integrating in the original space is extremely hard. Whereas if we can transform in the standard normal space, we can simply evaluate this quantity, which at the end only involves computing the distance between the origin and the plane, which will give us a very good approximation of our integral. Keep in mind, in the standard normal space, this is valid for ui independent of uj, meaning that we're in the independent standard normal space free from correlation. Okay, how can we then transform in that standard normal space? So given that we have an a-dimensional random vector where x is distribution like f of x, which is given, and we can have also the joint CDF, which from a theoretical standpoint is obtained by integrating the joint PDF. So then, given that we have a set of standard random variables, which is going to be of same dimension, so n, where we have its joint PDF, which is a standard normal PDF, and its joint CDF. So if we want to use a linear approximation to estimate the probability of failure, what we need is two things. The first one is we need a transformation from x to u. So t here describe my transformation. And we also need the inverse of such a transformation denoted by t inverse. The second thing we need is we need the Jacobian of that transformation. So j of ux represent the partial derivative of the transformation u with respect to the input x. So, so that means g of ux of ij is the partial derivative of ui, the output, with respect to xj, the input. And we are going to need that Jacobian in order to evaluate the gradient of our limit state function, because we're going to need to evaluate that gradient in the U space, the standard normal space. So that gradient of standard normal space, based on the chain rule of derivative, is going to be the gradient in the original space x times my gradient of x with respect to u. And keep in mind that the gradient of u with respect to x is simply the inverse of my gradient of x with respect to u. So I can flip from one to the other by simply taking the inverse. So now we're going to see the four common cases we're going to need in the context of reliability theory for our transformation function as well as for our Jacobian. The first one is going to be our standard or random vector is going to be the Gaussian distribution, so multivariate normal. Second case, we're going to have prescribed marginal, which can follow any distribution, but each dimension is going to be independent. So we're going to be able to model that joint distribution in the original space by taking the product of my marginal. Third case, we're going to have a joint distribution defined with the Morgenstern distribution. Fourth case, we're going to have our joint distribution described by a Nataf distribution. So first case, the simple one, we're going to have a joint distribution in the original space described by a multivariate normal or Gaussian. So we can say that here, in order to transform from the original to the standard normal space, I'm going to use the equality of the CDF, the cumulative distribution function. So f of x, the joint CDF in the original space, must be equal to the joint CDF in the correlated standard normal space, where r of xx is going to be here, the correlation here, it's still going to be r of xx. I did a little typo here. So here is going to be just r0. So u, my correlated standard normal space, is going to be equal to the Jacobian of u with respect to x, which in the case where x is standard normal, is going to be the inverse of my Cholesky decomposition of my correlation matrix times dx, x minus mx, the value minus its mean. So if I want to flip this relationship to go from u to x, is going to be u times the Jacobian of x with respect to u. So it's going to be the standard deviation matrix times the Cholesky decomposition plus the mean. And keep in mind that standard deviation matrix is a square matrix where I have 0 everywhere except on the main diagonal, where I have the standard deviation of each random variable. So here, if we explicitly represent the terms here, so jxu is the Jacobian. I can obtain this or by the inverse of the Jacobian of u with respect to x. This is going to be equal, as I said, to the standard deviation matrix times the Cholesky decomposition of my correlation matrix. So sigma xx, which is my correlation matrix, can be obtained by saying dx, standard deviation matrix, correlation matrix, standard deviation matrix. So, and Rxx is the, as I said, correlation matrix, and L is the Cholesky decomposition of that correlation matrix. And here, actually, it's not a typo. It's really, in this case, that standard normal space is going to be correlated by Rxx. And if we look at the transformation here, dimension by dimension, in red, I have my standard normal space for one marginal distribution. Here I have the original space. So both, in this case, are Gaussian. This one is zero mean unit variance. This one is whatever. So we can see that if we go by the equality of the CDF, so if we do it one dimension at a time, if I read the value for, say, here 3.4, I read the value of the CDF, I read the value of the CDF in my standard normal space, I invert this, I'm going to get 0.74. And if we would scan for all the possible values of x and corresponding u, we would see here, if we represent the CDF for the standard normal space, CDF for my original x, if we scan towards all the values, that relationship is linear. It's because these relationships are linear relationship. And this is only valid because my original space is Gaussian and the standard normal space is Gaussian. So I have a linear mapping between those two. We're going to see in all other subsequent cases we're going to see, this is no longer holding. So say for the second case, we have prescribed marginal for each dimensions, but these dimensions are independent, meaning that xi is statistically independent from xj for any I not equal to j. So it means that I'm going to be able to transform each marginal by simply using the equality of the CDF. So f of xi must be equal to the standard normal CDF of ui for all of my n dimensions. So ui equals the inverse CDF, if I simply send this on the left-hand side of the equation, of f of xi, the CDF of my ith original space or original random variable. If I want to flip this relationship to go from ui to xi, the standard normal CDF of ui inverse CDF of xi is going to give me my x space. Now, just like in the previous case, I also need my Jacobian. So the partial derivative of ui with respect to xi. In this case, this is going to be a diagonal matrix because all these transformations are one-to-one. I only have one ui for one xi. So u2 is not influenced by x1, say. So that's why my Jacobian is going to be a diagonal matrix. And each term of that diagonal, if I take derivative of these functions. So derivative of CDFs are PDFs. So it means that it's simply the PDF of xi divided by the standard normal PDF of ui. So these are going to be what I'm going to have on my main diagonal. And now, if we look at the transformation between, again, in red, the standard normal space, and the original space in blue, which is not Gaussian anymore. So this is Gaussian, zero mean unit variance. This is not. So if we look at the relationship between these two, we see that now it's nonlinear. And that relationship, again, represents the same thing, equality of CDF. Meaning I'm going to read a value in my CDF here for the standard, the original space. So if this is 2.09, I read the value of the CDF, I go to my standard normal space, read it back here, I'm gonna get here 0.74. And if I would scan for all these values between in red, the standard normal space, and in blue, the original dimension or the original space, I would get that nonlinear mapping. And that nonlinear mapping is because standard normal space is Gaussian, original space is not. So the relationship between the two that we obtain from these equality of CDF is not linear anymore. So the third case we're going to see is what happens if we have a known joint distribution that is modeled using the Morgenstern joint PDF that we saw in detail in module 3. So in such a case, we can model that joint PDF by the product of conditional distribution and a one marginal, where we can do the same thing with the conditional CDF. So conditional CDF of xi with respect to all the input variable. This can be obtained by integrating our conditional with respect to the ith variable we want to obtain. We would do that integration from the lower bound up to xi, the variable we want to evaluate. And this allows us to represent the transformation between the original space X and the standard normal space U using what is called the Rosenblatt transformation. So we transform our first dimension by the equality of CDF. Then we're going to transform our second dimension by the conditional CDF of x2 knowing x1. And we're going to do this for every dimension, always for all dimensions higher than 1 using the conditional CDF. And we can revert this relationship going from the standard normal space ui up to xi by doing the same thing. So the first one is going to be equality of CDF, and then we're going to have conditional CDF given the previous dimension. And all of these analytical expressions can be obtained fairly easily using the Morgenstern joint PDF and CDF. So if we want to first compute the Jacobian from xi until ui, we can obtain the first one from x1 to u1 by simply derivating the equality of the CDF, which is going to give me a ratio of PDF of x1 divided by the standard normal PDF of u1. So for all the other dimension, for all I less than j, we're going to have 0. So meaning that for all the lines, so for all the inputs that is smaller than j, so for all the upper triangular, I'm going to have 0. Then for all I equal j, my main diagonal, I'm going to have this term. So it's going to be equal to my conditional CDF, conditional PDF xi divided by the previous, given the previous variable, divided by the standard normal PDF of ui. For I greater than j, so my number of lines greater than number of column, I'm going to have this term here. So this is going to be the partial derivative of the conditional CF xi given the previous variable divided by xj, and I'm going to divide here by the standard normal PDF of ui. So this Rosenblatt transformation has the caveat that it depends on the ordering of the random variable. You choose a different order for your random variable, you're going to get a slightly different formulation for your transformation. But in practice, we can obtain all these derivatives, although it seems to be complicated. We can typically obtain fairly simple analytical formulation when we model that joint distribution using a Morgenstern distribution. So the fourth case we're going to cover is the Nahtaf distribution. So we're going to say that we're going to assign prescribed marginal to each of the ith dimension, which can follow any marginal PDF. And we're going to know what is the correlation matrix between our dimension. So we're going to build a jointly Natta distribution for these marginal and that correlation matrix. So this is the most common case used in the context of reliability. So if we know those marginal distribution, we know the correlation matrix, we're going to model that joint using a Natta distribution. So for the Natta distribution, we need to make two types of transformation, going from the original space X to Z, Z being a correlated standard normal space, and from Z to U, going from that correlated standard normal space to the standard uncorrelated space. So if we look at this visually from a graphical standpoint, we have X or original space. We can have prescribed marginal and we can have some dependency. So this is going to be my n-dimensional X space. In this case, it's going to be simply two-dimensional. Then if I want to go in the Z space, so it's going to be a standard normal space, so mean 0, standard deviation or variance 1, but where I can have correlation, I simply transform one-to-one my distribution from X to Z by dimension using the equality of the CDF. That's going to bring me in my Z space where I can still have correlation. Then if I want to compute my probability of failure, I need to go into U space. To go into U space, I need to remove the correlation from this space. And I do this by multiplying my Z space obtained here by the decomposition, the Cholesky decomposition for my correlation matrix here. So the inverse of that Cholesky decomposition. I can do the reverse path going from that standard normal space, U, and I want to obtain Z. I'm going to simply multiply these U by the L0, Cholesky decomposition of my correlation matrix here. And if I want to go from Z to X, I'm going to use the equality of the CDF dimension by dimension. This is what was already leveraged by the Natta distribution that we saw in module 3. So if we go in more detail for modeling the Natta distribution, so we're going to say, we assume we know what is the PDF for each of my marginal dimension. I know the correlation coefficient with any pair of dimension. And I'm going to be able to use the equality of the CDF to say I can go from a xi to a zi by saying the CDF of xi, CDF inverse of the standard normal CDF. So if we use the change of variable rule, we know that we must maintain the probability content in the two neighborhood from the X space and the Z space. That means from a mathematical standpoint, using the change of variable rule, that f of x dx must be equal to f of z dz. So the probability content in the X space must be equal to the probability content in the Z space. If I send dx on the right-hand side, that tells me that my joint PDF I'm looking for is the standard normal joint PDF divided by dzdx, or dzdx is actually the Jacobian of the transformation from z to x, so the derivative of z with respect to x. And if we apply this, that joint PDF is going to be a standard normal joint PDF with correlation matrix R0. And the Jacobian here is basically the determinant of my Jacobian. The determinant of that Jacobian is diagonal. Determinant of the diagonal matrix is going to be the product of the term of the diagonal, where each term of the diagonal is going to be the ratio between f of xi, the PDF of xi, divided by the standard normal PDF of zi. So the only thing that we're missing to apply this formulation is how do we define R0, my correlation matrix. So that R0 is a correlation matrix in the standard normal space. So correlation is defined by this bi-dimensional integral of xi minus mu I divided by sigma I, xj minus mu j divided by sigma j, times the two-dimensional PDF of zi, zj. So in general, I need to evaluate that rho 0. I don't have a closed form solution to do this. I need to do a numerical evaluation. So in module 3, we saw that we have some polynomial approximation of that inverse resolution. Modern computer code, such as Pistra, Pyrel, or Ferrum, will do that numerical integration for you. But in general, that correlation coefficient in the original space is larger or equal than the original correlation coefficient in the X space. So if we want to go from the original space X to the standard normal space that is uncorrelated, we need to multiply these univariate transformation by the Cholesky decomposition of our R0, the correlation matrix in the standard normal space. So that's going to allow us to go from X to Z. X to U. Where, as I said, L0 is that Cholesky decomposition of R0. And Zi is the correlated standard normal space. So if we want to reverse that transformation, we can simply say from Zi to X is going to be the CDF of Zi, the CDF inverse of that quantity. And if we want to go from Z to U is simply multiplying U times that Cholesky decomposition. So the inverse of what we add here. And the Jacobian to go directly for the partial derivative of ui with respect to xi. So that compound Jacobian is obtained from the chain rule of derivation. So it's going to be the partial derivative of ui with respect to zi, zi with respect to xi. So the Jacobian from u to z is simply that L0, what we have here. Okay, so the inverse of that Cholesky decomposition. The partial derivative of this with respect to this is simply that linear factor times the Jacobian of z with respect to x is going to be equal to what we have here. So it's going to be a diagonal matrix of a ratio between the PDF of xi divided by the standard normal PDF of zi. Okay, so that sets the basics for form, the first order reliability method. So we're going to look at a quick introduction, and we're going to see a complete formulation. And in order to be able to compute our design point, where we're going to linearize or limit state function, we're going to review the IHLRF algorithm that will allow us to find that design point. So given that we know the joint distribution for x, and given that we know the limit state function g of x that define the limit between our failure and our survival domain. So the first order reliability method form will allow us to linearize g of u, or limit state function. And we're going to do this linearization at u star, the most likely failure point, or what we always also call our design point. So how do we do this? First, we're going to transform g of x, or original limit state function, in the standard normal space. Then we're going to approximate this limit state function by a plane or hyperplane. We're going to make the linear approximation at the most likely failure point, or the design point. And this is akin to what we already saw with the FOSM method. So in module 5, sorry. And when we saw this in module 5, we were assuming that joint PDF here was multivariate normal. In this case, we're not going to do that simplification anymore. We can admit any joint PDF for our formulation. And that's going to be a lot more representative of the distribution of my random variable. Because remember, in the context of reliability theory, we're looking for fairly small, or reliability theory for structures, we're looking for fairly small probability of failure in the order of 10 to the minus 4. So in that case, our probability constant is going to be far out in the tail of the distribution. And by choosing one PDF or another, we're going to have drastic change in the probability constant in the tail of the distribution. So that's why choosing a multivariate normal is not going to be a representative choice, because this one has a very low probability constant in the tail, which might underestimate the probability of failure. So if we look at the formulation of form, so we're going to see that the formulation is entirely analogous to what we saw with FOSM. Okay, what we want to do is to approximate our limit state function in the standard normal space. So our g of u, we want to approximate, in this case, the limit state surface by a line, or the limit state function by a plane. So to do this, we're going to say my g of u, which is really a nonlinear function in the standard normal space, is going to be approximated by first order Taylor series, which means it's going to be the evaluation of my limit state function at u star, my linearization point, plus the gradient evaluated at the linearization point times my standard normal random variable minus my linearization point. And keep in mind that if we're doing that linearization on the limit state surface, so the limit state function on the limit state surface must be equal to 0. So that first term drops. So what we have is, what if we distribute the gradient into that parenthesis, is going to be the gradient times my random variable minus the gradient times my linearization point. And here that gradient, keep in mind, is the gradient with respect to u, standard normal space, is equal to the gradient with respect to x times the Jacobian of the partial derivative of x with respect to u. So now that I have that linearized limit state function, I can directly propagate uncertainty to compute what is going to be the mean of g of u. So the mean of g of u is going to be the constant part, so minus gradient times u star. And the variance of g of u is going to be gradient times the variance of u. So variance of u here is going to be identity matrix times gradient transpose. So that here is going to give me simply the square of the norm of my gradient vector. So beta, as we saw, the distance between the original and the point here, is going to be equal to the ratio between the mean of GU divided by the standard deviation. So this is equal by, if we divide what we have here by the square root of what we have there, is going to be the negative normalized gradient vector. This is going to be alpha star times u star, my design point. So if we want to write that in a shorthand, it's going to be alpha star, alpha hat times u star. So keep in mind that alpha hat is that negative normalized gradient vector, which is equal to the gradient divided by its length with a negative sign. And u star is my design point, so the point that is the most likely failure point that is going to be on my limit state surface. So the point that is on my limit state surface, and that is the closest to the origin in the standard normal space. So we have our alpha vector, which is perpendicular to my limit state function and limit state surface. And we have our u star. The point is on that limit state surface that is the closest to the origin. So now the next question we need to answer, and this is the same thing we did already with FOSM, how do we find u star, our design point? So there are no closed form solution to do so. We must use the IHLRF algorithm in order to do so, that improved Azopher-Lind-Rachwitz-Fiesler algorithm. So which is similar to the Newton-Raphson algorithm, which is going to iteratively refine our approximation of where is that design point. So we're going to start with a classic choice of saying we're going to start at the origin in the standard normal space. So in that case, if we evaluate our first order Taylor series where we're linearized at the origin, g of ui for ui equals 0, or integral choice, is not going to be equal to 0. So as we did in the previous slides, we cannot cancel this term anymore. So we need to keep it. So now if we want to regroup all the terms that are constant that are going to be involved in the calculation of my mean value, so I can regroup them. So my beta I at the current linearization point, which is the origin, is the mean term divided by the standard deviation. So we're going to have this term here, which is the mean, divided by the norm of the gradient. So if I regroup the terms, so g of ui divided by its norm, which I have here, gradient negative divided by its norm is going to be that alpha vector. And I know that I can obtain my subsequent linearization point by saying I'm going to simply multiply my negative gradient vector that points towards the failure domain by my current beta that I approximate. So my new point is going to be simply what we have here, the beta that is approximated there, times alpha. All quantities I can compute at each iteration. The problem with using this in a naive way is that we might not converge because these iterative algorithms, such as Newton-Raphson, might diverge. Okay? It's because if we have, say, a Newton-Raphson algorithm that tries to find the root of a function where it's equal to 0, if we evaluate this function by a first order Taylor series approximation, and we set it equal to 0, I'm going to find this point. This point, I'm going to do the same thing. First order Taylor series expansion, I'm going to set it equal to 0. I'm going to find this. And I'm going to converge to the final solution. But in this case, the issue is that if instead of having this solution, that one would lead me there, then I would diverge, because when I would set it equal to 0, I'm not find this one, I'm going to find another root of my function. So the same can happen with this IHL alpha solution. So the solution, what I can do is I can say that my new linearization point is going to be equal to the current one plus lambda, a scaling factor, times the search direction, where the search direction is simply the proposed point by multiplying bi times my negative normalized gradient vector minus the current linearization point. So if I take the difference between two successive linearization points, the one suggested by the product of beta times alpha and the current one, this is going to be my search direction. And lambda, my scaling factor, can be between 0 and 1. 1 is that I directly accept to move to the proposed point. 0, I want to strongly reduce, or I want to stay where I'm currently at. So how do we are going to decide what scaling factor we're going to use? We're going to use a merit function that measure, are we progressing towards our goal of being on the limit state surface and being the closest as possible to the origin. So as long as we're going to decrease the value of our merit function, we're going to say we accept to move. If we don't decrease between two successive iterations of our merit function, we're going to say we don't accept to move in that direction. And a merit state function that will allow us to guarantee that we converge is this following form. So we're going to have 1/2 times the norm of u, so the distance between u and the origin, plus c times the absolute value of my limit state function. So I want to make sure that I'm getting closer to 0, and I want to make sure that the norm is minimized. So c is a constant here that satisfies this ratio. So as long as we can pick any arbitrary c that satisfies this function, we're going to be guaranteed to converge. So theoretically, we could optimize lambda I to minimize that merit function, but that's going to be as complex as finding u in the first place. So we typically don't do so. So what we're going to do in practice is that we're going to verify that our merit function decrease. If it doesn't, we can say divide lambda by 2. And we're going to successfully do this until we satisfy that the merit function between two successive iterations decreases. And we're going to do this until we converge. And how do we define convergence? We're going to have a first criteria, which is going to say that the ratio between g of ui and the original g at the origin in absolute value is smaller than a tolerance, that we can say it's going to be 10 to the minus 3. And the second one is that the difference between two successive linearization points must be smaller again to 10 to the minus 3. So if we satisfy those two criteria, we're going to deem that we have converged. So if we apply this to our 4 cases of transformation, the first one is going to be for the joint distribution, which is going to be multivariate normal. We're going to look at the transformation function. How do we apply the form method there? And what are the results? So we're going to take our classic problem. We have a component, which is a bar, subject to a solicitation S, and where the resistance is modeled by d square f of y. F of y is um, the elastic limit of my material, and d square is the cross-section area. So I can model g of x, my limit state function, as r of x, so d square f of y minus my solicitation. So the mean and standard deviation for d, mean and standard deviation for s are given, d and s are independent. So I can have my two variable, x1 is d, x2 is s. I have my mean vector, my standard deviation matrix. My correlation matrix is identity matrix because I have no correlation. My Cholesky decomposition, same thing, identity matrix. And I can have my gradient vector of d of g of x with respect to x1 and x2 given by D's formulation. I can compute my Jacobian, so the inverse of my identity matrix times standard deviation matrix. If I invert this, I'm going to have a Jacobian of x with respect to u. To transform from x to u, x minus mx times the Jacobian of u with respect to x. So the product of my Cholesky decomposition inverse times the inverse of my standard deviation matrix. Transformation from u to x, so u times dxl plus the mean vector. So the steps to follow if we want to find our design point. We start from u0 at the origin, which corresponds to the mean value in the original space. Then I'm going to compute the value of my limit state function at the linearization point, which corresponds to the evaluation of my limit state function in the original space. So it's going to be 15. Then the gradient of my limit state function in the original space can be the gradient of my limit state function in the original space times the Jacobian, which is going to give me this value. I can compute alpha, my negative gradient vector, standardized vector, is going to be that gradient of ui divided by its length, which is going to give me this number. So my search direction is going to be beta times alpha. Beta is given by this quantity times alpha. This is going to be my new design point as proposed, minus the current point, which is 0, 0. That's going to give me my new search direction. I can compute my new point with lambda equal 1 as my current point plus lambda times my search direction. And I want to verify that between two successive steps, my merit function is decreasing. And in that case, if I compute this quantity is equal to 0, I can choose my constant here to compute my merit function equals to say 10. It's greater than 0 is going to satisfy that I'm going to convert. So if the merit function doesn't decrease from u1 to u0 or from u0 to u1, I'm gonna divide lambda by 2. Otherwise, I carry on with lambda. And I'm gonna restart at step 2 with the new linearization for the new point that's gonna be defined here. If we do this successively, we're going to say x0, x1, x2, we already find our optimal point, which is here. We can see that we've linearized the limit state function in the standard normal space. We can evaluate what is our beta, 1.28. Standard normal CDF of minus beta is going to give me my probability of failure, 0.1. So this is exactly equivalent to what we saw in module 5 with FOSM. Keep in mind, form and FOSM, in the case where our joint PDF is normal, are going to be exactly the same. However, this is not equal to MCFOSM because at MCFOSM, MC stands for mean center, meaning we're not linearizing at the design point, we were linearizing at the origin in the standard normal space. Second case, what do we have if we have prescribed marginal for xi, xj that can follow any distribution, but these xi, xj are independent, meaning we can model the joint PDF by the product of the marginal. So we're going to see the marginal CDF, we're going to see the transformation, and we're going to see the results. So we got, again, the same setup, but now x1 is modeled instead of being a Gaussian, it's going to be a log normal, and S solicitation is going to be a Gumbel. We're going to assume that these two are independent. So we have, again, the same setup for our limit state function, the derivative, and the variable. So now we have the probability density for the second variable, which is going to be a Gumbel, meaning that we're going to need to go from the mean of our random variable to the parameter mu and beta. So we need to solve this system of two unknown two equations. So that's going to give us for mu and beta 12.8 and 3.9. Now, if we want to go from x to u and vice versa, we can use to go from x to u, the transformation by the equality of the CDF, and or Jacobian is going to be equal simply to the ratio of the PDF of xi divided by the standard normal CDF of ui. We can reverse these relationship by inverting for the Jacobian the Jacobian we have here, and we can simply reverse the order of these CDF equality. So if we apply that same thing, we're going to have now a probability of failure of 0.08. And notice the difference between what we had before. So here what we have is the original space where we have a nonlinear limit state function. And since we have a nonlinear mapping between the original space and the standard normal space, now you can see that the limit state function is now more linear than it was here. It's because we have a nonlinear transformation between the two. But keep in mind that this here gives us a very good approximation of our linear approximation in the standard normal space. Is going to give us a very good approximation of our failure domain. However, it's not always a guarantee. In this case, it ends up that we're transforming our space in a way that favor us for minimizing the approximation error. But we have no guarantee this is always going to be the case. But keep in mind that what we do with form is that we do a first order approximation in that standard normal space. And since we have, in a general case, a nonlinear transformation between these two, it's not because we're doing a linear approximation here, that's going to be linear in the original space. So we can see here, represented in cyan, is my form approximation in the original space, which is not linear anymore. So this is something that we must always keep in mind. Other thing is that if in my origin, my mean is mx, the corresponding point in the space U is not necessarily the origin 0, 0. Again, it's because I have a transformation between the original and the standard normal space. Third case, what do we do if we have a joint distribution? That's going to be described by a Morgenstern distribution. So what are the transformation rule and result? So we're going to have, again, the same setup, but now with the log normal for the dimension and a gumball for the solicitation, but we're going to have a joint Morgenstern distribution with a correlation coefficient of 0.3. So in that case, for the log normal distribution, I have my parameter going, I should have done it for the previous case, but I want to find the mean and standard deviation in the log transform space from the mean of the variable and its coefficient of variation. That's going to give me these two parameters being equal to 2.28 and 0.2. I do the same thing for the gumball to find the same two parameters I had previously. Nothing changes because it's only the information about the marginal. Now I can model the joint CDF using the Morgenstern distribution that we saw in module 3, and I can obtain the joint PDF by differentiating this term, which is going to give me this analytical formulation, where if I want to obtain the conditional to represent my transformation function from UI to xi, this conditional CDF is obtained analytically by differentiating this expression, which is going to give me this term. Where if I want to represent my alpha term in these expression, is going to be equal to the correlation coefficient in the original space divided by 4 times qi qj, which can be obtained by the table that are available in the module 3. In this case, it's going to be equal to approximately 1 because we're at the upper bound in terms of correlation coefficient of what we can model with the Morgenstern distribution. So the distribution or the transformation between the original space and the standard normal space is going to be modeled by the Rosenblatt transformation. So first dimension is the equality of the CDF. Second one is the equality of the conditional CDF for x2 given x1. So the transformation from u1 to x1 can be obtained by reversing this distribution. But this second transformation from u2 to x2 cannot be obtained directly. So here, if we want to obtain the equality of the CDF, so CDF of U2 equals to that conditional CDF. Conditional CDF is obtained by this quantity here. We need to have a numerical resolution to infer what is f of x2 because it depends on what was previously obtained for x1. So we need to obtain the solution according to the first resolution for x1 that we obtained for the first dimension. So we need to solve this sequentially. So x2 cannot directly be found directly. We need the value of x1 in order to evaluate what is x2. So the Jacobian is obtained by this. Here we have here the ratio of PDFs, the ratio of conditional PDF and marginal PDF, and we have this term here which involves the derivative of the conditional CDF and the marginal PDF of U2. We have 0 in the upper triangle, where what we have here is the partial derivative of the conditional CDF is obtained by this analytical expression, and we can obtain all these fairly easily with the Morgenstern distribution. What we can see here, we have our joint PDF. We can see it's a nonlinear limit state function. We transform in the standard normal space. We have that, again, nonlinear transformation of our limit state surface. And here our probability of failure is 0.04. We, again, linearize our limit state function, limit state surface at the design point. And when we transform back to the original space, it's going to again apply a nonlinear transformation. So both are our form approximation. It's linear in the standard normal space. It's not going to be linear anymore in the original space. Finally, the fourth case we want to cover is really the one that is the bread and butter of reliability theory applied to structure. It's going to be a joint probability density function modeled by a net distribution where we know the marginal and we know the correlation matrix between our random variable. So what is going to be our transformation in marginal and what is going to be our result? So again, same problem setup. Now we have D, which is log normal, S is Gumbel. We have a 0.3 correlation coefficient between R2 and the same setup what we had previously, except that now our joint distribution is with a net half distribution. So we have again the same transformation for the parameters for the log normal, for the Gumbel. Nothing changed from our previous results, except that now we model the joint by a net half distribution. So we're gonna have a standard normal correlated space times the Jacobian of the transformation, where the R0 is obtained by, or in this case, polynomial approximation of my R0, which is going to be my original correlation coefficient, times this polynomial approximation, which can be found in module 3 for the log normal and Gumbel marginal. So that's going to give me my rho 0, which is 0.31. So my R0 is going to be 1 on the main diagonal, 0.31 on the off diagonal term. That L0, that Cholesky decomposition, is going to give me that lower triangular matrix. So the Jacobian between U and X, the standard normal space and the original space, is going to be the product of the two Jacobians. So the inverse of my Cholesky decomposition times the diagonal matrix, which represents the Jacobian between Z and X. So the ratio of the PDF for Xi and the standard normal PDF of Zi. So again, we go from original space X to Z, correlated standard normal space, to uncorrelated standard normal space. Here, I do a one-to-one transformation using the equality of the CDF. From this to there, I remove the correlation by simply multiplying by the inverse of the Cholesky decomposition of my R0 matrix. And I can do the reverse path going from U to Z by multiplying by that Cholesky decomposition. And I do from Z to X by the inverse of my CDF equalities. So if I apply this now, I have my joint PDF. I'm going to start my IHLRF algorithm at the mean. Mean will correspond to here a point that's different from the origin in the standard normal space. And then what I'm going to do, in a few iterations, I'm going to converge to my U star, my design point, where I'm going to linearize my limit state function. So again, that limit state function in the standard normal space will correspond to a nonlinear linearization in the original space because I have a nonlinear transformation between X and U. And now my failure probability is going to be equal, in this case, to 0.05. I can evaluate this by simply having my beta, and CDF of minus beta is going to give me my failure probability. If we look at what would have happened if I would have used a smaller lambda, say 0.25, you can see that here the contour we see are the contour of my limit state function that is out of the plane in that white region, is inside the plane in that red region. And we can see that what we found here at U star is my linearization point, and we can see that my alpha vectors follows the contour of my limit state function. So in summary, for form, in terms of limitation, the form method can be really accurate, really fast, but since it's gonna approximate my limit state function by a plane in the standard normal space, if my limit state function is strongly nonlinear, my approximation of form might either, in this case, overestimate or underestimate my failure probability. If I'm strongly linear, I'm going to be with a marginal approximation of, or a marginal error of approximation of my failure probability. But what we need to keep in mind is if my limit state function is strongly nonlinear, I might be having an error in my approximation of my failure probability. In that case, I can use either SWARM that we're going to see later on. A second order reliability method is going to consider that limit state function as being not a plane but a parabola. So I'm going to reduce my approximation error. Or I can use Monte Carlo integration we saw previously in module 4. And we're going to see also important sampling later on, I think in module 12. So one other limitation is when the number of dimension is large, the domain that contribute to the failure is not anymore centered simply on a design point. It's spread out in the large number of dimension, meaning that our approximation that is with low error around U star is not necessarily going to lead to a very good approximation of our failure probability. Nonetheless, for practical application, the form method has stand the test of time and is really the standard method that is used for practical application of structural reliability because it's fast and for most contexts of structural reliability problem is very accurate. So in summary, uh, the discrepancy between form and FOSM is the same basic procedure, except that FOSM will consider that the joint PDF for our random variable is going to be a multivariate normal, where form is going to assume that it's going to be any distribution, where FOSM can be seen as a special case of form. So in all cases, we need two things to transform from the original space to the standard normal space where we're going to apply form. So we need the transformation function as well as our Jacobian. So for the first case where the original space is normal, these transformation are linear function, and the Jacobian is simply the product of the standard deviation matrix times the Cholesky decomposition of our correlation matrix. For the second case where we have independent random variable that are prescribed or that are modeled by marginal distribution that can follow anything, we're going to transform from U to X by simply the equality of the CDF. The derivative for my Jacobian is going to be a diagonal matrix of the ratio of the PDF and the standard normal PDF. Third case where we use a Morgenstern distribution, in practice we don't often use it because the net distribution will allow us to model larger range of correlation, but we saw in the third case that we can do it with the Morgenstern distribution as well. And finally, the fourth case we saw is that if we model our joint distribution by a NetAF joint PDF, we can directly obtain the transformation from X original space to Z, the standard correlated normal space by the equality of the CDF. So here, and from Z to U by multiplying that Z space by the inverse of the Cholesky decomposition of R0, the correlation in the standard normal space. So this is the essence of form, the first order reliability method. So that is what we saw here. What we're going to see next is how can we use everything we saw here in form in order to conduct sensitivity analysis to see once we get our probability of failure and say it doesn't satisfy what is the code requirement, how can I act upon it? Which variable is the most sensitive with respect to the failure probability? On which parameter of those random variables should I act upon? We're going to see as well, how can we use the formulation of the form method in order to calibrate the coefficient that are used in load factored design. So the partial safety factors are used to scale down the resistance or scale up the solicitation. How can we calibrate those partial safety factor to achieve a given reliability target? So this is what we're going to see in the module 7, which is sensitivity analysis.